I'm going to give you actually a little bit of context on this. So example, two smooth pipes are supported by the let me get the problem statement, are supported by the forked by the fork you can just put it that way, of the tractor. We are asked to draw the free body diagram for each pipe and both pipes. Right, so draw the free body diagram for pipe A, draw free body diagram for pipe B, and consider both of them as one system and draw the free body diagram for both of them, for both pipes together. So we have to draw 3 free body diagrams. Each pipe has a mass of 300 kilograms. All right. So I'm going to go step by step. I'm going to start with the free body diagram for pipe. Let's see which one is easier. Let's just start with free body diagram for pipe B. For pipe B. I'm going to draw the pipe here. Let's put it right here. We have enough room. There you go. Let's say this is pipe B. All right, so we're isolating this. We're isolating pipe B. I'm isolating pipe B. What forces do I have there that I have to take into account? Tell me some obvious ones first. Like, what is the most obvious one that we know from before and there's nothing new there? Think about those 4 forces, 4 types of forces: springs, cables, and pulleys, smooth contact and support reactions, and weight. So which ones do we have on this? Give me one, then I'll take it.
Weight.
We have weight, exactly, Nathaniel. Thank you. So we have weight, and since it's, I'll tell you that since it's a ring distributed, right? If you don't know it, don't worry. It's not something I expect you to know, but similar to a beam or rod that you put in the center, when you have a circular shape that the shape is perfectly symmetric, the center of mass is exactly in the center. So you put the weight exactly on the center of gravity or center of mass. And it's always downward, obviously. So that's that. It's 300 kilograms, so it's going to be 300 times 9.81. Now, all right, that was the obvious one. What else do we have there? If you isolate this pipe B from its surrounding, what else do we see there? Do we have to put there? Right? Out of those 4,
a smooth contact force.
Exactly. Thank you, Diego. Smooth contact force. And a smooth contact force is always Want to remember this or write it somewhere, take a note. It's always perpendicular to the object at the to the surface. Sorry, that's the mistake you should make. It's always perpendicular to the surface at the point of contact. So here is the point of contact, right? This is your point of contact, right there. Another point of contact here. So wherever you have point of contact, smooth contact or normal force should be perpendicular to the surface at the point of contact. That means this is going to be your normal force on this one, and this is going to be normal force on this one. It's preventing this these contacts or preventing this pipe B from going down or going in this direction. So I'll put it, let's call this NB. This is a naming that might help later on, otherwise you can just call it whatever you want. NB, you don't have to follow my notations. N1. And that's pretty much it. All you need to take into account for free body diagram for pipe B. Now let's do for a little more challenging one. Let's do pipe A. Right. Let's do pipe. I don't call it challenging, but free body diagram for pipe A. Right. Remove this, erase this one, and then I'm basically isolating pipe A. Draw it here. If I can draw it like this circle, there you go. So forces on this one. Right. So what do we have?
Weight.
We have the weight, right? It's the straightforward one. Put it exactly in the center of mass. And as I said, if you have a symmetric shape like this, axis symmetric shape, center of gravity is in the center. So that would be W is equal to 300 times 9.81 newtons, whatever that value is. What else do we have?
Smooth contact force.
At which points?
On the bottom left and right side.
Exactly, all of them. Thank you, Diego. You pretty much said all of that, mentioned all of that. So we have a bunch of normal forces. Let's see where are the smooth contacts. There is one here. Not the best color. There is one. See if I can write a better color. There is one here. There is one here, and there is one here. Right? We're isolating this from everything around it. So wherever it has a contact with the surrounding, we have to put some smooth contact force. So in this case, we have this normal force. Again, smooth contact is perpendicular to the surface at the point of contact. So in this case, we have this. If I can draw it better, there you go. We have another one in this direction. And we have another one in this direction. Now, this one, some normal force, and let's call this NA. We can call this NA1, NA2. Right? Again, I'm just making up these names. You can just use whatever parameter. Remember, when on a free body diagram, a force should either be mentioned by a parameter or a variable, or should have the magnitude on it. If you know it, put the magnitude or value. If you don't know it, use a parameter to name it. But free body diagram has always have to have all the forces either labeled or with values. Now, the other normal force here, or smooth contact, A and B are in contact. Going to some fundamentals. Newton's third law, for every action, there is a reaction opposite and equal. So if the smooth contact force from A to B is N1, is it this one? This one. Then the smooth contact applied from B to A, the two objects applying force to each other, right? So Newton's third law again. For every action, there is a reaction opposite and equal. So if A's force on B, we call it N1, as a result, B's force on A also should be N1 because they should have the same magnitude, but in opposite direction. So that is in this direction, as I put here, and it's still N1. You got this part? You draw two free body diagrams, one for this pipe A, one for pipe B. Where they are in contact, nothing is moving, everything is in equilibrium, right? It doesn't matter even if they move. When they're in contact, where they are in contact, think about Newton's third law. For every action, there's a reaction. If this B is applying a force to A is applying the same force to B, opposite and in same magnitude, opposite direction. So the force between them is the same. On B is in this direction, on A is in this direction, opposite direction. That's why I used N1 for both. Right? We'll see this again and again when two things are in contact. Always keep in mind Newton's third law. Right? Wherever you put force on one, you have to go to the other one, and wherever they're in contact, the same force should be on the other one in the opposite direction. Especially when it comes to machines and frames, you'll see this over and over. So the last part, free body diagram for both. Which means I have to draw, that's gonna be tough, two circles next to each other. Let's see how good I'll make it. Yeah, I have to be in contact. Let's see if I can move this one. I can, oh, not bad. Okay, so think about this as A, think about this as B. Somehow they shrank. So now I'm isolating A and B together. Remember, if a system is in equilibrium, every part of that system is in equilibrium. Meaning that if a system is not moving, every part of that is not moving or in equilibrium, I have to say. So we can draw the free body diagram for every part. Two parts together, three parts together, just one part, one specific part of the system, doesn't matter. You have to be able to draw the free body diagram for every part of a system. Now, in this case, we're asked to draw the free body diagram for both A and B. So I'm going to isolate these two. This is my isolation line, right? Now, when we look at both, of course, we're going to have weight for both of them, right? This is downward weight. This is downward weight. Weight of each, I put in the center of mass or center of gravity for each. Yeah, I told you, we use center of mass and center of gravity interchangeably in this course. So this, you can call this W1, call this W2. I don't put the values here. We know W1 is 300 times 9.8, and W2 is the same, 300 times 9.8. We're given the magnitude, note for each. What else do I have there? I forgot to put the direction for this.
Smooth contact force.
I have a bunch of smooth contact forces, right? Like pretty much everywhere we have a contact. So here is one right there. Let me use the same color code. One is here. One is there. And another one is there. And remember, Smooth contact, the force has to be at the point of contact perpendicular to surface. This is your surface here. This is your surface here, right? This is your surface. This is your surface. So the point of contact perpendicular to surface. And there you go. This we called NA2. So I'm going to use the same naming. NA1, and we call this NB. This is the free body diagram for both of them. All right. I can actually give more information. Since this is 30 degrees, let's be a little more. This has to pass through the center. So this is 30 degrees. Here, these are passing through the center. We can think about this as 30 degrees of, think about this as 30 degrees. Or what else? This is 30 degrees. Just playing around with the angles. 30 degrees, 30 degrees, 30 degrees. This one in the one that we have for both. This is also 30 degrees. And same story here. I didn't do a good job drawing the angles, but this is also 30 degrees. Same story there. This is also 30 degrees.